I am nowhere as well versed as Joe or Nelson, but I'm glad I have them to back me up should I fall into a little rut.
No worries. We're here for you, buddy.
Okay, very good. So this is, I couldn't figure out quick enough how to turn the animations off. This is picture this, and it's all about schematics. So the name of an electrical wiring diagram using standard component symbols, that's the schematic. And this is a representation of all the different kinds, just a few, but a lot of the different kinds of symbols that are used in a schematic. The symbols on an electrical circuit schematic diagram represent electrical component connections. So, for example, component number 3 in figure T3, this figure, is a variable inductor. So, the variable inductor. The component number 4 in that same figure is an antenna. And I guess you can sort of make an antenna out of that, but you'll get used to it. You'll know what these are as you run into them in the future. A capacitor is used together with an inductor to make a tuned circuit. And here they're talking about series resonance and parallel resonance, where the minimum impedance at series resonance and the maximum impedance at parallel resonance, they each has its own schematic, not a diagram, but a symbol, there we go. And here you see to the right, inductor, which is just as Joe said earlier, coiled wire, and the variable capacitor to the right that he showed us a good example of. A simple resonant or tuned circuit consists of an inductor and a capacitor connected in series or in parallel, whichever it needs to be for the circuit you're trying to work with. So component number 1 in this here is, let's get that off the screen, is a resistor. And as Joe mentioned earlier when we were talking about, not so much squiggly, but this little diagram, this symbol it's doing its utmost to make things really hard for the electrons to flow. They have a lot of other things that are more roundish and more squiggly. So I think squiggly is the wrong kind of word. Jagged. Try running water through that pipe and see what happens. It's going to slow down. And component 2 is the transistor. And don't ask me if that's what kind of transistor that is.
Yeah. NPN, I say.
Because this is not my part of the ham hobby. It just, I get it. If I need to know it, I'll look it up. That's the cool thing about being able to look things up. All right. I knew it for as long as it took me to take my test, and fair warning, some of them come back in your general upgrade license. So it's not something you want to forget, but it's always something you can study right beforehand, which I really, really recommend for those who aren't into electronics or electricity. Okay, moving on. The function of component number 2 in figure T1 is to control the flow of the current. And component 3, you saw one of these before, but it looked different, but it looks similar. It's a lamp. I was going to point to it.
Yeah.
If you remember, it was more like a squirrel a loop. And so you'll see that every once in a while, a symbol may not be exactly the same, but usually it's close enough to something else that you've already used to get the idea.
Hey, Bill.
Sure.
Oh, well, I'll tell you what. You go ahead and finish that last bullet. I did want to talk about that diagram off to the right for a second, because this is a neat opportunity to talk about how a transistor works.
Okay, great. So as you can all read, component number 4, battery. I think we saw a battery before, and Joe and Nelson, they're the ones that you really, they are the authority figures here. So I'm going to step aside and go ahead, Joe.
Okay. Well, over on the right-hand side, everybody, you can see that's a depiction of a very, very simple transistor circuit. And it consists of a battery over there, number 4. That's a symbol for a battery. You've got a small lamp. You have a transistor and a resistor. Now, how that circuit works is that, and these are simple things, it's really easy to breadboard these things together. And as you get into ham radio, I encourage everybody to fiddle around and experiment with these, even the simple circuits, and see how they work. In this one here, imagine that battery number 4 over there. Let's say it's like a 6-volt lantern battery or something like that, or a 9-volt battery would be fine. Number 3 is a light bulb, and then you have the transistor. Now, if nothing is happening right now when you hook all of that stuff up, nothing's going to happen. The light's not going to come on. The way the transistor works is you can see that number 1 resistor. Over to the left of it, they depict a little symbol there that looks like, imagine that's a connection. How a transistor works is that if you apply a relatively small voltage or current across that point to ground, and that's from the base to the emitter, that tiny bit of voltage there acts like a switch, and it will allow current to flow from the battery up through the light bulb and then down through the transistor, and that's when the light will come on. So it's that little bit of voltage that gets applied from the base to the emitter, and that's over, like I said, that's where the 1 is and where the arrow points out of the transistor. A tiny bit of change in voltage there will allow the larger voltage along the back side of that to flow, and it'll make the light bulb come on. And that's something that, again, as you get into this a little bit more, you can experiment with just a couple of batteries. You could use like a AA cell to create the voltage across the resistor there in the transistor. And as you connect and disconnect that 1.5 volt battery, your 9-volt battery will cause that light bulb to come on. Okay. Anything to add to that, Nelson?
No, that's a pretty good description. Yeah, the transistor in this case is acting like a switch. Transistors can also act as amplifiers if you arrange them a bit differently.
Yeah.
But yeah, the key thing about a transistor, I think, for your license is a transistor can have gain in the circuit. A little bit of voltage, a little bit of current can be turned into a big voltage or a big current by the transistor.
Yeah. Okay, thanks, Bill.
Certainly. Okay, so moving on. Let's go ahead and get to the next slide. There we go. So even I can explain this. A single pole, single throw switch is represented by component number 3 in figure T2. And you can see it, it's right there. The switch is one way, it is off. There is no connection. If you throw the switch the other way, it's going to make a connection between here and here via this little doodad. It's one of the easier ones to figure out without really knowing any electronics at all. So this is my friend. Whenever I saw this on my test, I was happy, let me tell you. But so that's a single pole, single throw switch. Now, a single circuit which switches between one of 2 other circuits is accomplished by a single pole double throw switch, which is, again, the same concept. It's not turning between on and off. It's choosing between one or the other circuit. So component number 4 is a transformer. And a transformer, oh my gosh, it's used for so many things, but mainly in what I look at it as is to usually to drop the current from what you, let's say, coming out of the wall to something lower that your device, whatever it might be, can use to power it. But it can also be used, I believe, to raise the current, but we're getting outside of this particular portion, and I'm going to let the experts talk to that maybe later on. Number 6 is a capacitor. Now, this, don't know why it has the straight bar and then the curved bar, but that one I found it was an easy one for me to actually remember and hold dear to my heart. Number 8, that's a light emitting diode. Looks very, very similar to a regular diode symbol, but then you have to the right of the arrow and the bar right here, you have your little light symbols, your little lightning bolts, I guess, is a way to, that's what I think of it as. So that's how you know it's a light emitting diode, these two lightning bolts there to the edge. I'm sure there's a technical name for those, but it's a light emitting diode symbol. And component number 9 is a variable resistor. You can tell that one's sort of easy to figure out. Your resistor is there. Remember, that's the squiggly marks that aren't so squiggly, making things hard to flow from one end to the other. And then it comes back around where this is sort of, let's say it can move from between here and here and here. How it does it, that's above me. But it can do it, and that's why it's variable. I just look for this. That'll help you a lot in finding the resistor part of the name, and then the rest you should be able to figure out. So a meter can be used. Can we watch the microphones?
Yeah, hey, John, I think it might be you.
Me?
Yep.
I'm not sure who it is, but it's
there we go.
Yeah, it must have been TV or something. Anyway, sorry, and thank you very much, John. So a meter can be used to display a signal strength on a numeric scale, and we've all seen these types of, not necessarily these types, but we all are familiar with how a meter scale reads. In something or another, you've seen one. Electronically controlled switch, that describes a relay. And then the relay is used to control something else. A regulator is a type of circuit that controls the amount of voltage from a power supply. The component commonly used to change 120 volt AC house current to a lower AC voltage for other uses is the transformer. So you've probably all seen something like that, whether in your television, heaven forbid you ever got back there when it was a high voltage television, or a radio or something. We've all probably seen one at one time or another. So the name of a device that combines several semiconductors and other components into one package, that's an integrated circuit, or better known commonly as an IC. So here we go, folks. 5 watts increased to 10 watts is a power increase of 3 dB. And it is as it says, it's important to know about decibels because they are used heavily in electronics. The decibel is used to describe power change or change in power by levels. It's to measure the ratio of power output to power input. And once you get a hang of it, it is relatively simple to calculate a dB power change. So the thing to remember, every time you go up or down 3 dB, well, let's stay with up because that's what the chart's doing. Every time you go up 3 dB, your power change is going up by 2. So at 3 dB, you have a 2 times power change. 6 dB, a 4 times power change. So it doubles from the last set of dB. So it gets a little bit tricky. I might ask for help later on, but it's not going to ask about 20 and 30 and 40 dB. It's going to stay with 3, 6, 9. I might hit 10. I don't think it did on my test, but that was a while ago. But the important thing is you go up 3 dB, your power's going to usually double. But when you get to magic numbers like 10, it gets a little bit more complicated, which is something I can't really fully explain right now. After I look it up and figure it out, I could, but that's, like I said, not my part of the game. So a power decrease from 12 watts to 3 watts, that represents a power decrease of -6 dB. An increase from 20 watts to 200 watts, looking at the chart over here, represents a power increase of 10 dB, 10 times. I'm pointing at the screen like you can see my finger. Okay. So a device commonly used as a visual indicator is an LED, and we know what the symbol looks like, right? It's a diode with 2 little flashy points to the side. Forward current causes an LED or a light emitting diode to emit light. Okay, here we go. Now you should all be able to do this. Another way to specify a radio signal frequency of 1,500,000 hertz is, this is one, but there is another way. Does anyone know the other way? Okay, 1.5 megahertz. It's not on the slide. I'm thinking, where is it? They didn't give me that answer. Well, it's true. Again, this is simple. You know, move the decimal point the appropriate numbers of places to the left or to the right, depending. Again, if a frequency readout shows a reading of 2,425 megahertz, it can be read as 2.425 gigahertz. It can also be read as a lot larger number with a smaller unit, like kilohertz or, heaven forbid, hertz. But we don't want to do that. We want to usually go to the lowest common denominator, gigahertz, because it's just easier once you get working with it to round to the largest unit. Just like let's say you talk about dollars instead of how many pennies you have. It just works better. There are 1,000 volts in, does anyone remember? Kilovolt. And kilo, I mean, if you watch any drug shows on TV, we should all know what that one is. And that's what I do. I just go with kilo as my base and mega as a million, and I sort of go back and forth from there. If an ammeter calibrated in amperes is used to measure a 3,000 milliampere current, the reading would show 3. 28,400 kilohertz is equal to 28.400 megahertz, correct. And 500 milliwatts is equivalent to 0.5 watts. And 1.5 amperes is the same as 1,500 milliamps. Now we're getting past what I actually understand. So we're going to 1 million picofarads is equal to, I think, 1.5, no, 1 microfarad. Now, I don't know where I got that 5 from. Sorry. 1/1,000,000th of a volt equals 1 microvolt, I believe. Yes, very good. Some of it's coming back. And here is the table that I followed for a long, long time. Now I don't have it up so much because I don't need it. But in my experience, deca, hecto, kilo, mega, giga, going upwards in scale, getting larger, was easy for me. Getting smaller, that was a little bit trickier for me. So that you might want to make that table your friend until after the test is over. Rosin core solder, that's the best type of solder for radio and electronic use. Acid core solder should not be used. Acid core solder, you don't ever want to use that on electronics. There we go. So a grainy or a dull surface is the characteristic appearance of a cold solder joint. I know from experience.
Yep, happens to everybody at some point.
Yeah. All right. Voltage and resistance measurements are commonly used using a multimeter, or if you want, multimeter will work too, but multimeter is just the way I pronounce it. And this is an analog multimeter and next to a digital multimeter. I believe that inside they're more or less the same. It's just the readout that's different, but I could be wrong on that. But they do the same thing. So you want to make sure that you take precautions when measuring circuit resistance to ensure that the circuit is not powered. Sometimes it may not matter so much. You may get false readings, but other times, if you're working around really, really high voltage electrical units, like a tube radio or a more antiquated radio, although the oldies are the goodies, you can end up laying on the floor, maybe forever. So you really want to make sure that when you're working on equipment, it's not powered, whether it's a low voltage or a high voltage situation. Measuring voltage when using the resistance setting might damage a multimeter. Okay, just remember that. I don't have a good example to sort of bring that back to. Maybe Joe or Nelson might be able to.
Yeah. Well, on that one there is the way that a multimeter works to measure resistance is it does apply a small amount of voltage across the device. And the ohm meter is intending to just detect, a small amount of change. So if you have something that is powered and has a higher voltage, it could damage the circuits within the multimeter.
Oh, okay. Gotcha. I'm sorry. Oh, what happened?
No, I think you might be at the end of your slides.
I believe. Okay. Well, I missed one. Here it is. When an ohm meter connected across an unpowered circuit initially indicates a low resistance and then shows increasing resistance with time, That indicates that the circuit contains a large capacitor, because capacitors do take a little bit of time to charge up fully. And yes, picture this is over. That wasn't so bad. I apologize for things that I wasn't able to explain a little bit better, but thank you, Joe, and thank you, Nelson.
Mm-hmm.
And let me just go ahead and stop sharing my screen.
Okay.
There we go.